things of reducing the storage, the size of the box of soil organic matter gets bigger. So that's the general idea. So I guess I wanted to now really kind of highlight what I would call sort of the 4 key principles about soil carbon sequestration that we need to keep in mind. And the first one is that the duration of carbon sequestration is finite. So we're looking for, obviously, we're looking for long-term solutions to increase carbon dioxide in the atmosphere, but there is, certainly a limitation when we're looking at carbon sequestration. The soil carbon balance tends towards an equilibrium at which it comes basically that inputs equals outputs, and so the storage doesn't change then after you've influenced some of those fluxes. So as a finite duration. And the other point is that we can't add carbon indefinitely to the soil. There's a limited amount that's possible. The carbon content of the soil is subject to saturation. And then the kind of important point to keep in mind from the standpoint of practicality is that soils that are depleted in soil organic carbon have the greatest capacity to gain additional carbon, but often those soils have the least propensity to do so. And then finally, to keep in mind the issue that the gains, so you can increase soil carbon storage, but those gains are reversible. And so in order to maintain any gains you make, the practices have to remain in place, essentially. Okay, so what do we need to know in order to estimate this technical potential? So first thing we need to know is how does the carbon sequestration work? And yeah, we just learned that, right? So everyone understands that. We've got our soil carbon balance, and it's really pretty simple. So we know how does it work. The next thing we need to know, though, to calculate this technical potential is really what's the potential rate of carbon accrual that different management practices, different land use practices can provide us, and moreover, how do those rates vary by soil type, by climate, and over what duration can they occur? So this is really the kind of the rate question, if you will. And certainly there's a lot more we have to learn there, but I would say, in my judgment, overall, we have reasonably good knowledge of how soil carbon responds to management practices. This is a slide that was taken from a table that Pete Smith and company had in their 2007 paper in the Royal Society proceedings. And basically, the point about this is that we have a lot. Certainly we have uncertainty about carbon dioxide, methane, nitrous oxide. All of those are greenhouse gases that are of concern for agricultural management. But we have generally a pretty good understanding of how all these different practices really affect the CO2 or the carbon balance of the agro-ecosystem. So I think we're certainly know enough to make some reasonable approximations. So then the third thing that we need to understand is really how much of the land area can these practices potentially be applied over. And that's to do essentially an assessment of the technical potential. That's not really that hard of a job. We know the total land area of the Earth. We can stratify that into climatic zones and soil types, and we know the land cover and land uses. So we can do sort of theoretical what-if calculations. We know the land areas that are involved in that. It's, of course, a much harder issue when we're trying to understand what the actual potential might be under a given economic or policy environment, because then the land area that's actually available for these practices is a huge question. Okay. So basically, with those three things, one can go through and do these kind of estimates of technical potential. And here's a table that shows a yeah, kind of over the last 20 years. These are out of publications in the literature. The first one that I'm aware of was actually one that I was involved with as part of the IPCC's second assessment. It was first published, Vern Cole and several of us published a paper in '96, and then I was the lead on a follow-up paper in '98, and we estimated then that on the order of about 1.5 to close to 3.5 billion tons of CO2 per year was a potential rate. And then, you can look down the table, further, and you can see that Rattan Lal and Jim Bruce, and then a special report, IPCC 2000, Rattan again in 2004, the paper I mentioned in 2007, Rolf Sommer and Deb Bosio a couple years ago published another paper, and then last year myself and several others published a paper in Nature looking at this. And I guess what I'll show here is, yeah, the values vary a little bit, but in a way it's surprising convergence over a 20-year period that the numbers aren't all that far off, and it depends on, of course, there's lots of dependencies, but in general I would say there's a pretty good consensus that of this technical potential, it's relatively significant, and it's certainly not as large as global emissions or anything like that, but it represents a significant proportion, and therefore it's worth worrying about. I took a slide out of the Nature paper to illustrate one thing that I think is a fairly important one, and you can see on this slide, if you look at the vertical axis, it shows the area in terms of millions of hectares that these practices could potentially be applied to, and then looking on the horizontal axis, you can see the rates per hectare of carbon dioxide removal, if you will. And what I think is comes out of this is you can see that there are some practices that yield quite large per hectare decreases or increases in carbon sequestration or decreases in greenhouse gas emissions, but those are typically only available to practice on a relatively small area of land. Whereas if you look in the upper left-hand corner, there are practices that can be applied very broadly across a high proportion of the managed lands globally, but the average removal rates or average carbon sequestration rates there are relatively small. So that's I think an important characteristic to keep in mind. And we came up with this, somewhat higher than some of the previous estimates, but I guess I would point out that this, 4 to 8 also included there's a couple of practices that hadn't been in previous estimates. One was the fairly widespread application of biochar that could be produced from bioenergy, and also the development of crop systems that would have higher carbon inputs through their roots, so enhanced root phenotypes. So I guess the take-home points that I'd like to give here is I think that we really know enough about the technical potential. So we've been looking at it 20 years. No one has come up with a wildly different estimate, and I think the main point is it's big enough to matter, potentially, right, if we can capture that potential. So let's kind of move on from there. And I think what we really need to focus on now, more importantly, is to figure out how we can realize some of that technical potential, and that's really then looking at, what are the economic and policy potentials, if you will. So how do we devise effective policies? How do we improve the quantification at local scales where we might have mitigation projects or supply chain initiatives or other things that would contribute to mitigation? And how do we do this with transparency and low transaction costs? And then how do we really incentivize the folks on the ground, the farmers and ranchers that have to get this done? And I wanted to finish up then with the final slide that is one derived from our Nature paper last year that kind of looks at three different areas of R&D, if you will, or future work. And one is looking at sort of the science and technology, the other is the implementation, and then knowledge about what practice is. And I think what we need to do is, roughly lumped into three categories. And one is to improve this quantification technology, and there's a number of things that are put up there. Implementation strategies, building tools, building markets to do this. And then finally, I think it's all about incentivizing, how do we incentivize the best practices? How do we, reward the folks on the ground for doing the work to sequester carbon and reduce greenhouse gases? Okay, thank you for your attention. And now I'm going to see if I can pass back, or somebody else, can they take back me?
I'm on. I'm going to see how we can do this. Thank you so much, Keith. That was great, and you really pulled it off, winging it a little bit here with our technology. Yeah, I think that Austin's computer froze up with the 300 people on the call. I'm going to change the presenter to Jean-François. This means, Jean-François, that you will need to advance your own slides. Let's see if we can make this work. Okay. Here we go. Are you unmuted? I think you are.
Yes.
And
thank you, Betsy.
And thank you for for being so adept. Here we go. Thank you.
Thank you. So following Keith's presentation, I'm glad to introduce a way of developing a science policy interface. And this is a so-called 4 per 1,000 initiative, Soils for Food Security and Climate, which is obviously about soil carbon sequestration. As mentioned earlier by Betsy, the pledges for the Paris Agreement on Climate do include agriculture, forestry, and land use. At least 25% of the total committed mitigation is in this sector, with 128 countries that have contributed to pledges that also include restoration of degraded soils. It is important to have this in mind when we consider the results of the agreement, where there is a gap in emission reduction, since by 2030, even taking the conditional pledges from countries, there is a gap of 12 billion tons of CO2 equivalents that prevents reaching the targeted +2 degrees Celsius global warming threshold, not to mention the 1.5 degrees Celsius limit. So here we can think that soil carbon sequestration is indeed a major option for climate and for food security. Let me try to explain why, also taking the food security and climate change adaptation angles. First, when we look at the way you can increase yields in developing countries, especially starting with degraded soils, you realize that the improvement of the agricultural practices both increase crop yields and increases soil organic matter. With colleagues from the CGIAR, we have recently calculated that on average, although there is quite a large scatter in the data, if there is, with those trials, an increase by 0.4% per year in the soil organic matter, you get a large increase in crop yields. So improving the soils and improving the yields come together. Then if we think, and you all know this, about this large reservoir of carbon in the soil organic matter, we realize it's 2 to 3 times more carbon than in the atmosphere. And as mentioned just now by Keith, at least 1.4 billion metric tons of carbon could be stored annually in agricultural soils, so croplands and grasslands. And that is just slightly above this relative annual storage rate of 0.4% per year, which was used to establish this so-called 4 per thousand target. And I should mention that this was calculated by reference to topsoil. You could take it by reference, for instance, to 0 to 40 centimeter depths for the topsoil. Further, we know from work by Pete Smith by the IPCC and more recently by group with YASA that the economic potential could be close to 80% of the technical potential, assuming that we have high prices per ton of CO2. For instance, $100 US per ton of CO2. Then we have to consider, and this is on the next slide, the impacts of such a soil action on the global carbon cycle. So on this slide here, you have a vision of what could be the global carbon cycle in the 2030s based on the Paris Agreement pledges. So the figure, which is in billion metric tons of carbon per year for emissions for fossil fuel and cement, which you can see on like the red arrow on the left side of the graph, is 10.9 billions of tons or gigatons of carbon per year. So that's still substantial. And it is not fully compensated by the land sink and by the ocean carbon sink. So we are left with an atmospheric growth in carbon dioxide. We cannot, with those pledges only, fully stabilize the atmospheric CO2. When we now consider the global carbon cycle with full implementation of this 4 per thousand target and associated actions in forest, we have a very different figure. If it is possible to reach the potential carbon sequestration in all biomes, that is agricultural soils with 1.4 billion tons of carbon per year, desertified and salinized soils with 0.9, and the forest soils with 1.1 billions of ton carbon per year. So this adds to 3.4 billions carbon per year, and this is the sort of value that was used in the IPCC and also by other authors like Rat and Lal. Then we can see that part of this potential comes with forestry management. And if you do have the regrowth of secondary forest, tropical forest, plantations, and agroforestry, you will have also an above ground carbon sink, which we estimate at 2.2 billion tons of carbon per year. So when you consider the sum of the below ground and of the above ground carbon sink, you see that you have a strong action on the global carbon cycle, reaching about 5.5 to 6 billion ton carbon per year. And this is on the graph compensating largely the emissions, as you can see when you look at how, in addition to the current sink, we create that large potential land sink that compensates the current emissions. So if you consider the topsoil stock, which is 860 billions of tons of carbon on a depth 0 to 40 centimeter, this plus 3.4 billions of tons of carbon per year added to the soil carbon sequestration is equal to this 4 per thousand rate, an increase by 0.4% per year. So in the next slide, I just show again the many practices we can use to improve soil carbon. And those are both in the cropland sectors, they are also in terms of the rangeland management, of the agroforestry, and the use of organic fertilizers, plus better use of water management combined to soil management. And all this is highly compatible with the land degradation neutrality target, which is set by the UN Conference on Land Degradation and Desertification. So some of you may believe that this target, this rate of increasing soil carbon by 0.4% per year is too high. Well, let's look at a recently published paper which gives a synthesis of long-term field trials. And on the vertical axis, you have the sequestration rate, which is calculated in per mil per year. So the target which we have with this 0.4% per year of 4 per mil is figured as the horizontal dashed line on the figure. And as you can see, there are many dots, many experimental results, which shows that indeed the relative rate of soil carbon sequestration in soils, which was measured over many years, was higher than the target. And as mentioned by Keith, when you start from soils with a low carbon stock, you usually get higher sequestration rate. So it's only with soils which are pretty rich in carbon, like above 80 ton carbon per hectare, that this rate of 4 per mil becomes maybe saturating for what can be obtained with the soil. Now, in the next slide, we can look at the duration from those trials. And you see that there is carbon sequestration going on for many years. It's certainly going on for 30 years, but even with a few observed points, possibly 40 and 50 years. So it's maybe not possible to get universal conclusions from this data set, but it's very encouraging in terms of the potential. So let me go back to the co-benefits we're expecting for adaptation, land degradation, and food security. FAO in 2006 estimated that possibly half of the agricultural soils could be degraded, at least to some extent. So replacing fertilizers, replacing the nutrients which are lost by erosion through fertilizer is very expensive. It comes with a cost that has been estimated by the Intergovernmental Technical Panel on Soils between 100 and 200 billion USD. We also know that erosion is threatening soils. We are losing up to 1 billion tons of carbon through erosion from the agricultural land. And although this carbon could be stored later in sediments in the ocean, it is lost from soils and it is threatening the yields. So if we were able to restore the soil organic matter, we could get much better yields, at least in developing countries, as shown by that study by Ratan Lal, where you could get 24 to 40 million additional grains being produced by restoring the soil. And we have also some experimental evidence showing that soils which have been restored have less variable crop yields. So they may be actually better suited to increased temperature to climate change. Now, finally, I'd like to come to a global modeling study we have recently done with YASA, and that will be soon published. It is looking at the consequences of global greenhouse gas mitigation in the agricultural sector, not only in terms of the carbon that is not emitted, but also in terms of the food security. So you have here 3 sets of bars for the 2 degrees Celsius target. On the left, you have mitigation only with nitrous oxide, methane, and with forestry actions in green. Then you introduce in the mix of mitigation options the soil carbon, and this comes with a brown bar, brown vertical bar. And it is with the bar mentioned SOC, soil organic carbon. And finally, consider an option where you add to the soil organic carbon the yield increase which is associated to it. And you repeat this exercise with the 1.5 degrees Celsius target, where you get more mitigation in the sector. So what I would like you to focus on is on the red triangles. Those red triangles are read on the right scale of the axis, and they refer to the calorie loss. So let me take the example of the 1.5 degrees Celsius target. Without soil carbon in the bar where it is marked none, you would get, if you had really that level of mitigation in the sector, you would get calorie loss in developing countries by more than 300 kilocalories per day. So this would really mean in some densely populated countries like India and others, that food security would heavily degrade. In contrast, if you use soil carbon sequestration in the mix of options, the impacts on food security are far less because you are increasing the yields and you're preserving agricultural land because you are subsidizing those land for producing and for storing carbon. So obviously, soil carbon sequestration is not a
I'm just interrupting momentarily just to ask you to move to wrap up. It's going very, very well. Thank you so much. Thank you.
So I can go quickly here because it was already mentioned that storage will not last forever, that we will need to carefully monitor the soil organic carbon stock. We need to have enough phosphorus, nitrogen to store carbon. And during questions, maybe I can answer how we can get those nutrients in while sequestering carbon. And we need to carefully combine the soil and the water management. So last slide is about what is this initiative. It is both an international action plan, the 4PML, and it is also a global research program. Its objective is to increase soil fertility thanks to carbon sequestration in soils, with both impacts on improving food security, adapting to climate change, and mitigating greenhouse gas emissions. So we have here in that initiative 200 signatories with 38 countries and provinces, 11 international organizations, foundations, NGOs, research bodies, and universities, farmer organizations, and businesses. And maybe I can tell you more on how this is developing, answering your questions. Thank you for your attention.
Thank you so much. And I want to just, of course, underscore some of the co-benefits that Jean-François spoke to, which we can get to in the Q&A, but this is a very important point around food security. I want to remind people that we're not using the hand mechanism on your taskbar, but rather the question, there's a question mark, and if you have a question to pose to any of the speakers, you can just type it in at any time. I want to move to Eric Toensmeier now. Eric, I'm going to change the presenter and give you control of the screen. Here we go. You should have it now.
Okay.
Okay, we're just doing a good job. Thank you, and I'll just turn it over to you for the next 8 minutes or so, and then we'll have the last bit of time for some questions.
Great. And are those slides showing up okay?
Yes, they are. I did want to mention one thing. In one of the questions, it was very fundamental. I just want to mention that, and this was something for non-experts. We got a question on one of Keith's slides. It talked about PG. What is that? And so just to be clear, 1 pentagram is the same as essentially 1 gigaton, which is the same as 1 billion tons. So these are interchangeable terms used to talk about the amount of carbon that can be sequestered. So turning it over to you, Eric.
Great. Well, good morning or good afternoon, good evening or good night to everyone, and thanks to Betsy for having me. Let's see, well, I'll be walking through some of these similar topics, looking at sequestration rates, carbon stocks, adoption, and impact. So let's see, I'll begin by looking at sequestration rates, and again, this is the annual rate of sequestration of carbon in tons of carbon per hectare per year, and this includes both soil and biomass. And as we go through here, we'll see our numbers lean a little higher than some of the ones we've been seeing before. Some of that's because we're including above ground biomass, and some of that is because we're leaning heavily on some of these agroforestry type practices. So here we can see that the rates of carbon sequestration vary quite widely between different practices. The blue bars here show reviews and expert estimations by people like Ratan Lal and P.K. Nair. The red shows the drawdown meta-analysis, this organization Project Drawdown that I'm working with in our book, which just came out last week. These are our meta-analysis results from there. And the green represents single studies where I just wasn't able to find additional data. So we can see that the different kinds of practices have different rates. And what tends to be the trend is that when trees are added, those rates go up. Like annual cropping practices tend to be somewhere around or below 1 ton per hectare per year. By adding trees to those practices, sometimes we can get 2 or 3 times more carbon. Grazing also.
I'm sorry, Eric, to interrupt. We've had a request, I don't know if you can do this, to show this in full screen mode because of the chart's quite small and people are having a hard time seeing the practices. Much better. Thank you.
I'll get this out of the way. Let's see. So grazing also gets a substantial increase by the addition of trees to create silvopasture, and it's not as though a higher sequestration rate means that a practice is right for a given site. There's limitations of soils and slopes and climates, as well as markets and establishment costs, levels of mechanization, scale of operation. There's many different factors at play, but the general idea is that we want farmers and ranchers and land managers to have a toolkit of practices that they can use, and where possible to do ones with the highest carbon that we can get out of it. So the general rule here appears to be more trees means more carbon, although many exceptions. That's just a general trend. Let's see. This slide is looking at carbon stocks. That is to say the total amount of carbon once the soil has reached saturation, when sequestration has gone on for a number of years and it's sort of topped out. Where is that level? And these are, again, expert estimations from Lal and Nair primarily. We see that for a lot of the annual cropping and grazing solutions, we're hearing numbers like 30 to 50 tons, although I just saw some nice ones in that last presentation, more like 100. And when we add trees to annual cropping, we go to more like 150 or 200 as a maximum, not meaning that that's what happens every time, but there's a higher sort of maximum potential. Silvopasture, again, when we add trees to pasture in regions where that's possible and appropriate, we can see quite an increase, up to 250. PK Nair, I wrote to him last week just to confirm, and he said that globally silvopasture, we're looking at stocks of around 60 to 250. So that's quite an increase. And then some of these more fully perennial systems like shade cacao or other multi-strata systems can be as high as 300. Certainly not always. In every case, there's going to be somewhere it's actually getting worse under bad management or less than ideal conditions or so on. But general idea, again, more trees, higher stocks. And this is only soil organic carbon. This is not looking at the carbon and above ground biomass, which can be in some cases very significant as well in some of these systems. So the next piece is to look at adoption. And this is really where sequestration rate becomes less important, because it's really about how many millions of hectares you can get going. So the on the left there, the red bars show current adoption. This is from Project Drawdown, our estimated current adoption in million hectares of these solutions, and the blue represents additional adoption by 2050. This is in our optimistically plausible scenario, which sort of assumes a near ideal policy environment. And a lot of these adoptions are based on existing adoption rates, or are extrapolated from existing adoption rates. So it's kind of fun to see what different people come up with for their scenarios. We tend to lean more heavily in Drawdown on some of the perennial and agroforestry systems like silvopasture, tree intercropping, tropical staple trees, but certainly a number of other solutions that have been talked about quite a bit today as well. And it's interesting to note that the mitigation impact, which is what we see on the right there, you can have a very large impact from a small amount of new adoption, as in the case of silvopasture, or nutrient management. Very broad adoption can have a relatively small impact. In this case, we're modeling a 10% reduction of fertilizer use in regions where fertilizer is over-applied. Let's see, and then to really look at the question here, on the left you can see within Drawdown we looked at a whole range of different sectors of civilization and what the potential impact of adoption of various solutions could be. You can see our total impact by 2050 in this scenario is 1,051 gigatons between transportation, energy, materials, land use, everything. And that agriculture was 169 of that, which is almost matched by our solution that looks at reduced food waste and diet change. There's a little piece in there on clean cook stoves as well. It's worth saying again that supply side solutions, reducing demand, reducing waste, has a really, really big role to play, including very much in the case of avoided deforestation, which is where a lot of that impact is coming from for those particular solutions. Let's see. Since we're mixing emissions reduction and sequestration, I separated them out, and you can see on the top right there, we're estimating 151 gigatons through agriculture by 2050, which is roughly the same as 41 gigatons of carbon, and with emissions reduction a further 15.6. And the annual rate from all these solutions combined in 2050 is 7.3 gigatons per year in above ground biomass and soil organic carbon. Right around that point, we start to see saturation getting hit from a lot of these solutions. We're estimating a 30-year period to saturation, and we're also not including the sequestration from any current adoption. We're just figuring that current adoption will call that already saturated. So our numbers come out a little bit higher, or quite a bit higher than some of the other folks. We're on the high end of Keith's estimate there, and that's really, I think, the impact of the including above ground biomass, and also looking, if you look back, we have a high emphasis on some of these agroforestry solutions, silvopasture, tree intercropping. Silvopasture in particular, we found a total impact by 2050 of over 30 gigatons, which is really huge and surprised me. And that's primarily based on looking at the amount of grassland that's humid enough to support some tree growth and the really very, very high sequestration rates. Let's see, what did we get for silvopasture? We came in around, I think it was 4.8 tons per hectare per year on silvopasture, including, again, above ground biomass and soil. So that's our contribution to the conversation today. And over time, over the next 2 weeks, we'll have our executive summaries up on the website, and eventually the models will go up as well to give people an opportunity to play with those, and all of our benchmarks will be up in those executive summaries as well. Our agroforestry numbers are higher than what one sees, let's say, from IPCC, but they're very much in line with the highly cited paper from Albrecht and Kanji back about 10 years ago or so. So I look forward to the discussion, and that's all for me.
Thank you very much, Eric. And we do have, maybe just about 10 minutes here for some questions, and we've received many great questions written in. We have to keep you muted because there are so many people on. I want to ask a question. Let's see, this person has left, so I'm not going to actually use that one. We have a question from Elsa Sanchez in El Salvador. And this is not really a technical potential question, it's a question that goes to the heart of the matter. If we know enough about the practices that foster carbon sequestration and retain it over the long term, what are the technical barriers to moving forward? What do we need to do to get this moving? Probably, if you all answer that, that'll be our only question. So would one of you like to take that on?
Should I try to answer?
Yeah, absolutely. Yes, Jean-François, wonderful.
Yeah, thank you. Well, we have to realize that farmers, to change their practices, to change their systems, have some costs. And it is not so simple to readjust a farming system to sequester carbon in soils or to have increased biomass in your farm. So that's where presumably you need some incentives and you need some knowledge. So the incentives, they can come from some funding, and this funding could be attached to carbon credits, or it could be attached to the value chain. And you also need to have not only the knowledge, but you need to have the capacity building process. So these are some of the main barriers. And what is very difficult with this carbon sequestration issue is that literally hundreds of millions of people need to be supported to get those changes effective and to have carbon sequestered in their soils.
Thank you for that. And we have another question more in the sort of the socio-economic category from Stephen Singer from CAN International, Climate Action Network International. I wonder how much carbon sequestration in soils could be enhanced with measures beyond those you've had in mind and studied, such as just dietary changes, if we could reduce meat, beef consumption, particularly from intensified agricultural production. wouldn't this make a big difference? Let's see, I assume lots of intensively used land for fodder production and converted grazing lands might not be used anymore and return to the original high soil organic matter and high carbon. So what about lifestyles? I'm going to give that to Eric.
Let's see. I think I showed a little piece of that in our last slide. It's absolutely a critical piece of the equation, and the IPCC has some very nice writing about that in the 2014 mitigation document, the chapter on agriculture. It's really big. It's not enough, but it's a really big piece. And in Drawdown, we found that diet change and food waste reduction were both in the top 10 solutions of all solutions across all sectors. They're just very, very powerful. Absolutely.
So that's probably for another call, but a critical one that several other people also asked about. For Keith, from Jonathan Sanderman, given most of the data behind the meta-analysis used to calculate mitigation potential, given that they come from a limited number of countries, are you confident that these average sequestration rates will apply to all soil climate combinations?
Okay, thanks, Jonathan. We have certainly the preponderance of data from temperate systems, but there's a reasonable representation, I think, from the subtropics, and moreover, I think some of our models are capable of making estimates that apply to the subtropics and the tropics as well. And it's kind of like Jean-François also showed the picture that and there's a big spread in terms of rates of sequestration depending on the various practices, but I think the meta-analysis at the global scale, certainly for kind of this bounding problem of coming up with a reasonable technical potential, I think we have enough data now, to do that, and I feel those technical potential numbers are reasonable, but I think we need to go beyond that. And I think your point though is, as we get into what Jean-François was talking about, how do we provide the support in terms of quantification, in terms of policies and incentives that trickle down, if you will, to the individual farmers in El Salvador and Africa and around the world that are going to be doing this. We certainly have more work to be done, and we need more information to improve our models and our estimates to support those policies. So again, I guess at the global level, I think we kind of have a pretty good idea, but your point is well taken, that as we get into an implementation phase, assuming we do, there's very clearly an R&D component to improve our knowledge, at local scales to make this happen. Thanks.
Thank you. We have several questions here about co-benefits. When you have practices like cover crops and crop rotation and application of compost and all the different lists that you've seen in these presentations, what are the other co-benefits beyond both making the land more resilient in terms of the structure of the soil, being able to manage for water, but also several of the questions are around the nutritional value of the food, the actual food productivity, and I think, Jean-François, this would be for you.
Thank you. I think we have pretty clear evidence that when you start with a soil which has been degraded, which has lost a lot of organic matter, restoration is extremely effective in increasing yields. And moreover, having more soil organic matter means that you have a better water retention, and also you have a better water infiltration usually. So this means that it will buffer climatic variability, and this will provide some stabilization for the yields. So that's, I think, what we know best. Mm-hmm. In terms of other positive side effects, we can mention biodiversity, because when we will have this soil restoration process going on, we will also restore the soil biodiversity. And when we think about the landscape management, then we realize that having mixed crops, having trees or woodlands in the landscape will greatly improve this biodiversity. So you also have co-benefits on that side.
Thank you very much for that. And I think we have time just for one more question here. This is from Elizabeth Black. Given the fact that the total amount of storage of carbon emissions is limited in soils, it's significant, but limited, what potential is there for soil building? Can we rapidly build new soils and thereby effectively increase the total amount of carbon sequestration projected, say, past the 30 to 50-year limit? And why don't I let, I don't know which one of who would like to step up for that, and then I guess we'll need to wrap. You could all speak to this if you want very briefly. Why don't we start with Keith?
Just real quick. So I think that's a good point. Jean-François showed in his slides in the 4 per mil initiative, looking at desertified and soils that have almost been abandoned for productive use. And I think there's some potential there. I guess a couple of personal concerns I have. I think it's not a huge area that exists, and moreover, some of the soils that have been very highly degraded are no doubt going to be very expensive to bring back into a more productive capacity and to have the capabilities of sequestering more carbon. So I guess my feeling would be that we should focus on the on the vast majority of lands and the moderately degraded and that's where our greatest benefits are going to come from.
Eric, would you like to step up on this one?
Sure. Well, just on the issue of overcoming saturation in general, my sense is that addition of biochar is one way to increase carbon in the soil above and beyond that saturation level, perhaps, although it's not really clear to me what the actual limits on that are. And in terms of above ground biomass, harvesting some products like timber and using them in long-lived functions like building homes or long-lived bioplastics and things like that and then permitting some new fast-growing growth to return at a high sequestration rate. That's a little bit of a way to get around it in the above-ground biomass. But I think it's just really important to look at the fact that this is a very limited solution, and it doesn't work without fairly transformative changes in other sectors of civilization.
And any final word from you, Jean-François, and then we'll just conclude here with just letting people know we're going to be able to get the audio link and so forth. But I do want to give you the opportunity as well.
Thank you. No, just a few words about what, in fact, are the global solutions to reach this 2 degrees Celsius or this 1.5 degrees Celsius. All those solutions which were assessed by the IPCC require negative emissions. That is the capture or the storage of atmospheric CO2. And apart from what we have been discussing, which is the soil or the biomass carbon sequestration, you're left with the plantation of vast areas of forests and then burning this to get energy, capturing the CO2, and having some sequestration in geological reservoirs. So with a lot of technologies associated to this very deep storage in the rocks. So I think that this is not proven, in fact. Those technologies are not proven. So unless we would be able to have this land-based and soil-based carbon sequestration, it is likely we are not going to be successful to meet the targets of the 2 degrees Celsius or the 1.5 degrees Celsius.
And that is a perfect final note for the webinar. We brought this together because it is our sense right now that there is tremendous and growing interest in the potential to sequester carbon biologically. Of course, there are other interventions that are being considered increasingly. But I did want to just let everyone know that we hope that somehow that we can stay in touch. Feel free to come on to the Breakthrough Strategies and Solutions website to get the audio link to go back to the conversations. We'll also have the slide decks and sharing other resources. And we want to bring your attention to the Food and Agriculture Organization, which will be releasing its final report momentarily. Maybe it's just out, but coming, I think, this week from their recent gathering in March on soil carbon sequestration and the potential. Looking also at issues like measurement and verification of carbon, another one of the things we need to tackle. But thank you to everyone on the call, and thank you especially to our terrific speakers for your leadership in the world. And it is a time to seize the moment, and we look forward to doing so with you. And with that, I think we'll end the webinar. Thank you so much.